Yeah, dear students, today I will demonstrate an experiment on fiber optics. So we will do in this experiment the basic characteristics of optical fiber, and we also estimate some of its parameters. The optical fiber experiment aim is to determine the numerical aperture, acceptance angle, power loss and voltage versus current characteristics. In the first part, we will calculate the basic parameters of optical fiber, namely the acceptance angle and numerical aperture. Before doing this experiment, I would like to give a brief note on optical fiber. You know that optical fiber is a thin flexible conduit made by a glass like dielectric medium, and it propagates optical signals by the principle of total internal reflection. Any optical fiber, if you consider it for practical purposes, we require three different parts. Therefore, an optical fiber consists of three important parts, namely core, the central part of the optical fiber through which light propagates is called core, and surrounding it we have another layer called cladding. Cladding helps to get total internal reflection. To protect core and cladding, we have a third layer called as sheath or jacket. In the construction of optical fiber, the refractive index of core is higher and the refractive index of cladding is less, so that when light transmits through an optical fiber, when it strikes core and cladding interface, it undergoes total internal reflection if the angle of incidence is greater than critical angle. The basic principle of light propagation in an optical fiber is total internal reflection. So we will now see how to calculate the numerical aperture and acceptance angle of an optical fiber. If you see, this is an optical fiber. So the upper part or outer part what you are looking at is only the sheath or the jacket. But inside this we have a connection is there. To that inside this we have a small opening which is leading to the emission of light, and that part is core part of the optical fiber. Here I am taking 1 meter optical fiber, and this fiber I use it to calculate its parameters, namely the numerical aperture and acceptance. But the optical fibers are generally made by using glass or polymers. So optical fiber core and cladding both are made by glass, then it is called glass fiber. If the fiber is made by plastic, then it is called plastic optical fiber, POF. Sometimes we have silicon cladded say plastic fiber, PCS fibers, silicon poly. So therefore there are different types of optical fibers. Now we are using here a plastic optical fiber made by PMMA. So polymethyl metaacrylate is the material that is used for making this optical fiber. This is fiber optics characteristic board. On the board we have a digital voltmeter, and here we have digital milliammeter, and we have a power meter to measure the power. And this is the circuit, and this symbol is for the LED which emits light, that is connected to optical fiber to transmit through the fiber. And this is the receiving module, and this is the transmission module. That means this is the input from which a light is given into the optical fiber, and the light passes through the fiber, and at the destination end we have the receiving module, and the receiving module gets the light after passing through the optical fiber. Now I will show you how to connect the circuit and take the readings for the first part to measure the acceptance angle and the numerical aperture. Yeah. Now I have switched off the power. I am not switching on it. Once I connect the circuit, then I power the board and do the experiment. To do it, first connect the circuit. To connect the circuit, I have to add meter M1 here, and this meter is voltmeter here because they marked it as M1, and I take a wire and connect M1 meter from here to this meter M1, and take another connecting wire, connect this terminal marked as M1 to the voltmeter here. I am connecting this. This is a digital voltmeter we have connected. Then take another wire, connect meter 2. So here they have marked meter 2, and this meter 2 is ammeter. In this case it is milliammeter. I am taking first terminal connecting to ammeter, and take the next and connect it to the ammeter terminal. So we have connected the 2 meters. Now I have to connect it the optical fiber. So this is the optical fiber I am taking, as I have shown it to you already. Connect the optical fiber to the transmission module. This is called transmission module. I will add this to transmission module and I screw this. Once I add this, the light starts coming into this fiber if I switch on the power, and it goes through this and it goes through this, and this is the 1 meter length optical fiber. I am connecting it to the receiving module, connected to the receiving module. This meter, optical power meter, is internally connected. There is no need for us to connect it. So I will tell you how to take the readings. Now I switch on the power. So power is coming. Meters are showing some values. They will show 0 because we have not given any input. So if I go to here, we have power adjustment. So if I turn this knob, the power will change and the meters will show readings. So but the first part I am not doing anything. What I am doing is, in this case, I put this maximum. If I put the maximum value of this, completely maximum value, then the light coming to the optical fiber will be maximum. So for first part there is no need to connect here. I just remove it. I will show you how the light through the optical fiber changes when the input voltage is coming. So you can see here the light coming out to this. So I keep this light the voltage less, then it becomes, see this, the intensity. So I am decreasing the intensity, it has moved very much less. So if I increase this further, so the light is coming, and see the light is becoming maximum intensity. This is the maximum intensity. So for the first part, to find numerical aperture and the acceptance angle, the intensity of the light coming out of the optical fiber should be maximum. To do maximum, I have to keep the power adjustment knob to maximum. Once I keep this to maximum, I have to connect the output of this to a numerical aperture jig part of it. So I add this to, this is numerical jig, aperture jig. So this will have here a stand through which you can add the optical fiber to this, and I am taking the optical fiber here, I am connecting this, and you try this. Once you make the nut tight, the light comes from the other side of this. This is the other side of this. You can see the light coming here also. The light is coming. The light is what we have used, the source is LED. In optical fibers, the light sources we use are either LEDs or lasers. Laser is a good light source for optical fiber communication, but LED is a cheaper one when compared to the laser. So the light sources used in optical fibers are either LEDs or lasers. Here we have used a red LED which gives red light of wavelength 660 nanometers. This is a source through which the light is coming, and that is passing through the optical fiber. So now look at this jig. Here we have a stand connected to it, and here there is a scale. You can measure the distance in centimeters, but we note the readings in mm. And we have a graph paper sheet like this. This is the graph paper sheet. I can keep this here at any known distance, maybe 1 centimeter means 10 mm, 20 mm, 30 mm, like this. If I see this, if I keep it close, you can see the spot of the LED on the graph paper. If I increase this, the spot size also increases. If I increase the distance further, the spot is spreading out. So I will take 3 different readings by noting down the distance at which I kept the screen, and also I make note down the width of the spot. The width of the spot. I will measure the distance from here, this end to this end, or from bottom to top. This is a circular spot, and I have to measure. Part 1, numerical aperture and acceptance angle. I have given the tabular form. We have to measure 2 parameters. As I told you, we have to see where the screen is placed, that is the length L. If I place the screen at 2 centimeters, I take the value as 20 mm. And after placing the screen here, I have to measure the spot width. So as I am increasing the distance, the spot width also is increasing. So first if I keep here, I will get the spot width from here to here. How many? See, from here to here. How many mm it is occupying? Because you know that for a given graph paper, this is 1 square centimeter. In 1 square centimeter, we have 10 parts. Each square, smallest square, is 1 mm. So therefore, you can calculate how many mm it is occupying either diagonally, okay, from this end to this end, or vertically from this end to this end. So therefore, I am using the tabular form like this. So the tabular form is this. But what actually a numerical aperture is? Numerical aperture is defined as the light gathering capacity of a fiber. How much light it is capable of gathering, and it will take that light from the source into the optical fiber. That parameter we call it as numerical aperture. But in terms of our experimental setup, numerical aperture is given by the formula W by under square root 4L square plus W square, where W is the spot width and L is the distance where you are keeping the screen from the source. And sine theta maximum, in this theta maximum is acceptance angle. And numerical aperture and the acceptance angle are related by numerical aperture NA is equal to sine theta maximum. If then I'll write sine theta maximum is equal to, or theta maximum is equal to sine inverse numerical aperture. So you have to find out at least three different readings, means keep the screen at three different distances and measure the spot width on the graph paper and note down the values, at least three, and using L and W values you calculate numerical aperture and enter the readings here. Once you know numerical aperture values, find sine inverse of numerical aperture, you will get acceptance angle. So acceptance angle is defined as the maximum angle made by the incident light with the axis of the optical fiber, which allows it to undergo total internal reflection, and thereby it propagates along the length of the fiber. For example, I am drawing here the optical fiber. This is the core part of it, and over and above it we have another layer which is concentric about the first layer, and this is the second layer, and we have another concentric layer above this, and this is called the sheath or the jacket. So we have three concentric layers. From the line that is passing from the center of the core material, we call it as the axis. This is fiber axis. Fiber axis. The first part we call it as core of it, which is a central part through which light transmits. The second part we call it as cladding. So cladding, or we will clad, is the part that gives total internal reflection, and the third part we call it as jacket, or we call it as sheath. So when light is coming and falling like this, now what I suppose is that the light is incident on the optical fiber making some angle of incidence. This is angle of incidence. Because it is moving from air into the fiber, core material is made by either glass or it may be made by a plastic, and in this case of our experiment the fiber is made by PMMA material. So it undergoes a refraction at this interface and the light hits somewhere here. This is angle of refraction. If the light strikes this core and cladding interface at an angle greater than critical angle, then only it undergoes total internal reflection, and multiple total internal reflection, it propagates through the length of the fiber like this. If I slowly start increasing I value from this part of it, as I am increasing I value, at certain value of angle of incidence, the ray strikes at an angle less than the critical angle, thereby that ray will not undergo total internal reflection. Therefore, there is a maximum angle with respect to the axis at which the incident ray strikes the core cladding at an angle greater than critical angle, and it takes total internal reflection. If I increase the angle beyond that, then it strikes the core cladding interface at an angle less than the critical angle, therefore total internal reflection does not take place. Similarly also I can take here the light ray goes and strike this. So therefore, as it is a three-dimensional one, the light ray can go like this, can go like this, can go like this. Therefore, we'll have a cone of light. So all those light rays which are going in this cone angle, this is called acceptance angle, maximum angle theta I'll call it as. All those light rays which are confined to this cone, they will be striking the core cladding interface at an angle greater than critical angle, therefore they undergo total internal reflection and light passes through it. This maximum angle that can be used to send the light into the optical fiber so that it will undergo total reflection is called acceptance angle. Therefore, we are measuring what is the maximum angle. So we first measure NA by measuring the values L and W, and I take three different values of L and corresponding values of W are noted down, and we calculate NA value and theta maximum value. Now I will show you how to do the experiment and how to record the values. So I am taking the first reading. So keep the screen containing the graph paper at 15 centimeters. This is 15 mm. This is 1 centimeter. This is 1.5 centimeter, means that this is 15 mm. I keep this here 15 mm. And I have to carefully note down what is the width of this spot. The spot width I am carefully noting down, and I find how many divisions the spot is occupying on the graph paper. I should note down it as W. So in mm, because each small square is 1 mm, and how many small square the spot is occupying, we have to see it from one end to other end. So now see, I am taking here, I am measuring the distance from here to here. So at 1.5, this is 1.5. The spot is occupying a, okay, this is the spot. Yeah, this spot is occupying, if I count it slowly, one, okay, in mm I have to write it. The value will be from here to here is 1, 2, 3. Likewise, if I count up to this end, this is around 17 mm it is occupying. Therefore, I write the first reading as the first reading. The screen is kept at 15 mm, and the spot diameter is now at 17 mm. Now I keep the screen at 20 mm. So I keep this one at 2. This is the 2, and that is 20 mm. Then I have, now I am taking the second reading for the first part. I am keeping the screen at a distance equal to 2 centimeters, that is 20 mm, and I will measure the spot width. Okay, so the spot width, the circular spot, we will get it as that circular spot we have to measure. So that circular spot with diameter from here to here I am measuring, and if I closely measure, that will be coming around 23 mm. So I now write down the second reading as the 20 is the length where we kept the screen, and 23 is the diameter of the spot. Now I keep the screen at a distance 25. So this is the 25. So I keep this at 2.5. And the spot width I'll measure. So the spot width, if I measure from this end to this end, okay, that will be around 29 or 30. So 29 it is. So I am writing this value as 25 as L and 29 as the spot width. So once you note down these values, use this formula, calculate numerical aperture for each and every reading. So you have one and okay, but we are calculating numerical aperture for a given optical fiber. As the optical fiber is fixed, the numerical aperture is also constant. So you should get almost these three values, nearly constant values or the same values. Then you take the average value. If I take average, that will be the numerical aperture of the optical fiber. Similarly, use this equation. Numerical aperture is equal to sine theta maximum, or the acceptance angle is equal to sine inverse numerical aperture. So I use this formula. Once I will get the values of this, I take sine inverse of this value, I will get this. Likewise, I will get 3. For a given fiber, the acceptance angle is constant. Therefore, you take average value. So you should write these average values in the result, as the numerical aperture of the fiber is how much you are calculating this value, and the acceptance of angle of the fiber is this. We have to note it. That is a result point of view. At the end of every experiment, you need to write the result. So from this table, we are getting two results. One is numerical aperture, the other is acceptance angle. This is the first part. I am again repeating the procedure of the first part. First, you just go to the board. Keep this knob maximum so that the light coming out of the optical fiber is maximum. Optical fiber is maximum. Then you connect meter 1 here, meter 1 here. This is the meter 1, connect the voltmeter. This is the meter 2 and connect it here. You have to connect here. I am not noting down the values of V or I in the first table. And connect the, this is the LED, the light coming, connect the one end of the fiber here to the first part. And connect the second end of the fiber where the light is coming through this. So see that you can see the light is coming through the optical fiber. Even I bend it, the light will come, okay, from this. So that's the guiding nature of the optical fiber to transmit the light. So I am connecting this here to the numerical aperture jig. I am connecting this to the numerical aperture jig. And you are keeping the screen at 3 different distances, and we are measuring out the spot width of the given optical fiber which is falling on the screen. So we will do the second part of it. The second part of optical fiber experiment is to find out losses in the transmission of signal while it is propagating in the optical fiber. There are various losses when the signal is passing through optical fiber, and some of these losses, or some of the important losses, are bending losses. When an optical fiber undergoes a bending in between in the line, then the light that is propagating through the optical fiber may not strike the core cladding interface at an angle greater than critical angle. Thereby, a part will be lost, and some part of the light, instead of moving in the and confining the core, it will move into the cladding. Therefore, we have lost a part of the light. The light which has gone into the cladding from the core is now not a part of our signal, and it is not going to propagate along the length of the fiber, and thereby the signal strength decreases and we have a loss. There are two types of bending losses, namely macro bending and micro bending. We are doing this second part of optical fiber experiment in macro bending case. A macro bending means that if there is a bend in the optical fiber while laying it in a given place, so the optical fiber, if this is the optical fiber, it must be straight, something like this. If I bend it something like this, so to take it from one place to another place, and if I just suppose this is a curvature of the bend, from the starting, if I take this is the bend radius This is the radius of the optical fiber small r. The optical fiber is so small that it is approximately the size of your hair. So it may be around, the core may be around, if you take maybe from 10 to 100 micrometers. So very small, very small. The bend radius is R is very large. If the bend radius is large compared to the radius of the fiber, it is called as macro bending, large bending, macro bending. So we will do the experiment to find out what is the loss due to macro bending. In addition to the bending losses, we have mismatch losses, we have signal losses, we have chromatic dispersion losses, and many other losses are there in an optical fiber communication. These losses we will discuss in detail in the class because we have one unit on optical fibers. Let us now do the second part of the experiment. Now initially while doing the first part, we have connected the optical fiber one end to the jig. I am now removing it and see that this is the input where the optical fiber is coming, also called as the transmission module. The light is transmitting through the fiber and I connect the second end of the optical fiber to the receiving end of it. This is the receiving end. See, when there is no signal from the source to the receiving end, the output meter is showing 0 value. Now if I connect this the optical fiber here from the transmission module to the receiving module, this I will get some value in the optical power meter. And see that while doing this experiment, initially I'll take the readings without bending the optical fiber. The optical fiber is this is fully stretched without any bending. This is without any bending. Now I will also take here 3 readings. So first reading, if you look at the tabular form, the tabular form contains the power meter reading P1 in microwatts. Now I will adjust the this optical power meter reading in microwatts to a fixed value by adjusting this knob. I'll adjust this knob slowly. By adjusting this knob, I adjust this value of this. See, it is slowly changing. I keep it on around, if I go on decreasing it, I keep nearly around 1.5. For first reading, I am keeping this as 1.5 constant. So by changing the input knob, you can keep this as, so I'm roughly keeping it as 1.5. Once I keep this as 1.5, I note down those values in the tabular form. The second part of it, this is part 2. Part 1 we have already done. In part 2, I note down the power meter reading as now I am getting it as, I am getting this as 1.5 or 1.6. So I write this as 1.6 microwatts. I need to convert this into dBs. dBs means decibels. In general, in communication systems, the losses or the signals are measured in terms of dBs. That is called the decibel per meter. Therefore, the formula to convert the value from microwatts to decibels is dBm, decibel per meter, is equal to, I will write 10 into logarithm of the power meter reading meter reading. Whatever the reading the power meter is showing in microwatts, because this is a microwatt meter, divide this by 1000. So in this case we have 10 into log of power meter reading is 1.6 microwatt. Don't convert into watts, keep it as it is, divided by 1000. You will get a negative sign here because this is 1.6. Therefore that negative sign also you need to write down. Now I will explain the procedure of taking readings. Initially we adjusted the value of the power meter at 1.6 and I have noted down the value here, and you convert this into dBs by the formula 10 into logarithm of power meter reading in microwatt divided by 1000, and you will get the second column. You should do calculations and then find out the value. Now I will make here one turn and I have to note down the power meter reading. What is this one turn? One turn means I make a one single bend. So for that I use a mandrel. This is called mandrel, and this mandrel I use it, and at the center of this mandrel I make one turn like this, exactly one turn. So I'm doing experiment for only single turn. You can do the experiment for 2 turns, 3 turns and so on, but I'm doing it is for only single turn. If I just take this single turn and see the power meter reading, it was decreased. Okay, so it is 1.6 we have adjusted, but when I make one turn, the value of this one has decreased to, so this is the one turn I have made it. So one turn if I made it, and this has decreased the power to 1.4, 1. Now it is 1.2. So I note down the value in this table. For one turn the value is 1.2, and again convert this microwatt into dBs by using the earlier formula. Now you call this as P1, this as P2, and if you subtract, I'll get loss in dB P1 minus P2. Once you will get P1 minus P2 the loss, you need to calculate alpha, which is called as attenuation coefficient. The attenuation coefficient formula is given by this. The formula is alpha is equal to 10 log to the base 10 P1 by P2 whole by L, where L is the length of the fiber. Here the length of the optical fiber is 1 meter. So you have to calculate alpha for each and every reading we are taking. So we are taking 3 readings in part 2 also. In the first reading we adjusted the power meter at 1.6 and we have taken the values. Now I change the power meter reading to different value. By changing this knob, I am changing the power and increasing to around 2. Now it is 2.1. So note down this as 2.1 in the tabular column. I am noting down this as 2.1 and convert this into dBs, and then I need to find out by making one turn. So I make one turn here again by changing the input. So I am just making one turn and look at the meter value. So it has fallen down to 1.4. So I make a note of that value as 1.4. So whenever you are making a bend, there is a loss in the power, therefore the output power is decreasing. Again calculate P1 minus P2 and attenuation coefficient alpha given by the formula. Now third reading, I will adjust this to 3 or nearby 3. See how I am doing it. I am just changing this value and I am adjusting this to 3, and I should note down after making one turn on the mandrel. So this is 3. Okay. I have just 3. I take this one, make one turn. If I make exactly one turn, I look at the value of the optical power meter. It has fallen to 2.5. So once I made one turn, you can see that that value has changed. So thereby I keep that as 1.6 here and calculate this. Once you calculate all these three, you have to take average of this, and this average value you need to write in the result part of it. So first part will have numerical aperture, acceptance angle, second part will give you alpha value as a result. Then we'll do the third part. Now I am showing you part 3. So part 3 is now about the variation of input voltage versus the variation in the output power meter. So output power. So I am taking this as part 3. This is part 3. In the part 3, I change the voltage, input voltage. I am taking here 5 readings. You can take more also. And I write now power output. The meter gives you in microwatt. I need to convert into dB as we did in the earlier table. Move on to this. I am now adjusting this value of the voltage maybe around, see this, if you see the current is also changing, the power also changing. If I change and keep it very small input voltage, the optical power almost becomes 0. Therefore, I am now going backwards. That means we have initially at the higher value, and now I am changing this slowly, and see that the power is around 0.5, okay, 0.2, 0.1. It maybe I am taking 0.1. Now I will now change the voltage and measure it. The voltage is 1.47. So I will note down the 1.47, the voltage value as 1.47. And corresponding value is 0.1 for the power. You convert into dBs. Now I change the input power. I increase this to maybe 1.5. This is 1.155. So I write the corresponding value of the optical power meter as 0.2. So I write this as, okay, I write this as 1.55 and I note down it as 0.2. Later, I again change the output voltage, input voltage, and I'm changing this to maybe around 1.6 and 1.68, and the corresponding value is 0.4. So I write here as 1.69 and the corresponding value is 0.04. And if I see again, I'll change the value to maybe around say 2. So I'm going to 2. Okay, 1.8 also I'll take. Yeah, it is 1.84. I note down it as 1.84 and the corresponding value is 0.7. So I note down this as 0.7. See the values. And again I'll change the value of this voltage to 2 volts. Yeah, I'm going to 1.92 volts. So if I go for 2 volts, 2.0 or 2 volts, then I'll write it 2 volts and the corresponding value is 1.1. And again I'll go for the one, if you see it, I extend the table by taking different as 2.1 I am adjusting 2.1. So for 2.1 the corresponding value is 1.3. Similarly, if I adjust this to 2.2, I note down the value of the output as 2.2. I adjust this as 1.5. I go on increasing this in steps of this 2.3. Okay. For 2.3 it is 1.8, and I increase this to 2.4, and I note that value as 1.9. Okay, still if I increase this value as 2.4, I note down the value as 2, and if I still increase this further to 2.5, I'll get value 2.2, and I'm increasing this to 2.6, then 2.4 I am getting, then I'll go to 2.7 voltage change. This is 2.7, then the corresponding value is 2.6. I will increase this to maybe around say 2.8, then the corresponding output meter is 2.9. If I increase to 3, I'm directly going to 3 now. You can see 1 point. So the maximum here I'm getting is this. Now these are the readings we have taken. So because the tabular column is small here, I extended the values up to this. So we started from 1.47, we have gone up to say 2.8. Now draw a curve between the voltage on the, so I'll draw a curve by taking voltage. Okay, I'll draw a curve like this. I take voltage on this and dB per power on it. You should get an exponential curve, something like this. It is not a linear curve, you should get an exponential. Instead of drawing here, you can better draw because the power will be shown in negative. You can draw curve, you'll get the curve like this. So once you get the curve, you can see that the power that is decreasing in the optical fiber is not linear. So it's a nonlinear behavior and maybe exponential behavior, because the power through an optical fiber, when it is passing a signal, we can write that value in terms of power input and power output as power output P0 is equal to power input. Output is always a fraction of input. It is not the complete, but this changes as e power minus alpha L, where alpha is attenuation coefficient and L is length of the fiber. So therefore we have here an exponential relation between the input power and output power. Okay, so you draw the graph and submit along with your record. I stop here and you practice yourself how to take the readings and how to draw the graph.